In this video, we'll cover the problem number of connected components in an undirected graph. Specifically, we're going to solve it using a depth-first search. So here, actually it's really more of a depth-first traversal, but it's often called depth-first search. Now here we have a bunch of nodes in a graph, and they're kind of related with our edges that we can see here. We want to count the number of connected components. So a connected component is a group of nodes that are connected, either directly or indirectly. So for example, 0 and 1 are obviously going to be in the same connected component because they're directly connected. But 0 and 2 can also be in the same connected component because they have an indirect connection through the node with ID 1. So we have one connected component on the left here and another connected component on the right. Here, this is all just one connected component because 0 is indirectly connected to 1, 2, 3, and 4. And 3 is indirectly connected to 0, 1, 2, and 4, and so on. So we simply want to count the number of connected components. Now, we could just count all of our nodes, but then we would be counting this component 3 times and this component twice. So what we want to do is make sure that once we have counted a connected component, we never count it again. And so whenever we increment our counter and say, hey, I just found a new connected component from some node, we should mark that entire component as visited. And then in future iterations, we just check if the current node has been visited, just skip. Don't increment our counter and don't do anything like that. In terms of marking our entire component as visited, we can do this using either a depth first or a breadth first traversal. But today we'll see how to do it using a breadth first traversal. So we can go ahead and get started coding this out. I'll switch this to an ES6 arrow function, and I'm going to rename n to number of nodes. Now here, we'll need a variable, num connected components, that'll be 0, and in the end, we're going to return that variable. Other than that, we're going to say iterate through every node, starting at 0, up to num nodes, and what do we want to do at each node? Well, we can say, I found a new node, so increment the number of connected components. We're going to mark the component as visited, so we'll have a function that does this. It will need the node, and it's going to need a graph that I've not built yet, and it's going to need the visited set that I've also not created yet. Now, the other piece of logic here, we should make the visited set first. I'll make some of these variables right now. So we'll have our graph, which is going to build our graph from our edges. We've seen this before, just building our adjacency list. And we'll create our visited set, set here. Okay, so one thing we want to know is if we've already visited a node, we should not increment our counter for it. So for example, when we iterate, we're going to do 0 through 4 for example 1 right here. We start at node 0, we say, hey, we've never visited this, so we found a new connected component. Then we mark 0, 1, and 2 as visited in this function. Then we go to 1, it's already been visited, so we skip it. We go to 2, it's been visited, so we skip it. We go to 3, it has not been visited, so we increment our counter. Now we have 2 connected components. And then we mark 3 and 4 as visited. Then we go to 4, it's been visited, so we skip it. And we get 2 connected components for this input right here. Okay, so this seems like it should work. We can go ahead and write our build graph and mark component as visited functions. I'm going to try out using a map today, just, I don't know, for some diversity. Doesn't constant edge of edges. I don't have like a particular opinion on which one is better between a map and a JavaScript object. I don't think it really matters that much. I think you're kind of free to do whatever you prefer. But today I'm just going to try it out and see how I feel about it. So you've seen this before. This is our pretty standard graph creation function. The only difference is I'm using map methods. So we can say if the graph does not have node 1, just set it to be an empty array. And then we can do graph.get node 1 dot push node 2. This is a little weird. I don't really like this. So I'll say node 1 neighbors is going to be graph.get node 1. And then we'll push to that. This is a little interesting. It's like this check here becomes easier when you use a map because you don't like have to do has on property. It's just a nice has, which reads really well. So it simplifies your work there, but then pushing becomes weirder, unless you want to do like graph dot. Well, I mean, I guess even if you do graph dot get node 1 dot push, that's still going to be weirder. So I guess there are trade-offs. But okay, now we should have our graph constructed, and we can write our mark component as visited function, which is really going to be the key here. And it's going to take in a node, graph, and the visited set. Now we'll have our 3 steps. We'll have our base cases. We'll have our process node. We'll have add neighbors. I'll save the base cases for last. So for process node, the question is like, what do we want to do for each node? Well, for each node in the component, we just want to mark it as visited, so we can just add it to visited. Then we want to get our neighbors, so we can say neighbors. Oops, it's going to be graph.get node. We'll iterate over each neighbor of neighbors, and then we can simply recursively call our function on the neighbor. So we come here, we do neighbor graph visited. Okay, now we can handle our base cases. So this is like, when do we want to stop? Well, imagine we start at 0, we go to 1, and we say, okay, or we say mark component is visited on 0. Then 0 says marks itself as visited, and then it says mark component as visited on 1. 1 marks itself as visited, and then says mark component as visited on 0, because it can go that way, and that's bad. We don't want to do that. So we'll say when we get to 0 for the second time, we should just skip it. So if visited.has the current node, just return. So now, when we're at the 1 node, we mark ourselves as visited. We go to 0. We just cut that off immediately. We go to 2, which is good. We keep going. Now on the 2 node, we mark ourselves as visited. We try going back to the 1 node, but 1 is already visited, so we mark ourselves, or we stop early. And so looks like this is what we want in terms of base cases. So, and remember the key here, especially with recursive functions, is that you want to assume that your recursive calls work exactly as you want them to. So here for on the 0 node, we mark ourselves as visited, and then we just magically assume that when we call mark component as visited on 1, it does exactly what we want. It marks the rest of the component as visited. We don't even think about how that happens. We assume it's completely magical and it just works. That's the key to being able to write the code for a recursive function. Okay, let's see if this works. No, neighbors is spelled incorrectly. Neighbors is not iterable. Okay, yes, so there's also a case where the node that we're currently on has no neighbors. So we'll say if not graph.get node, or sorry, if not graph.has node, then we can just return early. We don't need to do any neighbor checks. Hopefully that fixes this issue. Okay, great. Looks like that works. Okay, well that's all for this video, and thank you for watching.